Hello everyone. Today I want to introduce another tool that I've been making in the last week, which is the self pruning. Again, if you are using Unreal Engine PCG graph, you will know this node, which is pretty handy. What is this node doing here? Basically, it will pruning the instance, which is the point, based on their bounds. Here is our instance, and then after the pruning, you can see there is nothing overlapped. All of the instances are separate. There is no overlapping at all, which is pretty handy if you want to avoid the overlapping. So here we just distribute some points and instance them and do the self-pruning here. Okay, so under the self-pruning, we have two categories. So that's the camera culling. So let's ignore for now. Let's focus on the self-pruning here. First of all, we have some rules to keep. For example, you want to keep it from the smallest or the largest. Here, if we try to keep the largest, here we can see the instance are more larger than before because they are trying to preserve the largest one. So it will trying to check the condition from the last one, where is the largest one. Internally, it will sort the instance, and then after all the things, yeah, the order may be wrong. Yeah, the order doesn't matter because you're doing the pruning, so whatever. So let's keep the largest one or keep the smallest one. So there will be more small instance, or you can also do a custom properties here. So for example, right now the proxy shape is convex. So here the closure will give it the convex geometry for each of this. You'll see. You may be wondering, why this is 2D? Yeah, because we are currently in the 2D version. So we can run into 3D, but that one just a little bit laggy here. So you can see this is my proxy shape, which is a convex hole, and you can base on the convex hole to give them some random sort weight used to sort the instance internally. And yeah, the convex hole. This is the accurate result. This is the accurate method, but it is also the largest one. As you can see, it will take 1 second to generate to get the final result here. Let's change it to largest here. You can see their convex hole, there is no overlapping at all. Even you going very close, you can see they are not actually overlapping, which give you a very tight instance packing here. And this is the 3D version. You can also check the 2D version. This is very useful if you only want to print, if your point cloud or instance is on a flat plan. So 2D version is much faster than 3D, as you can see. It's almost 2 times faster, and that's because I toggle the fast option here. If you don't toggle it by default, the 2D will be 1 second, and the 3D will be almost 1.5 seconds, which is again a bit more lag. So you can use the 2D to proxy the shape and pruning it. So if you are working on a kind of flat area, so this one is much better because this one runs faster. And you can also use AABB here. You can say this is my axis aligned bounding box. But the result, yeah, there are still a lot of empty space as we can see. And it also kind of gave you the weird looking something like a grid because this is based on the axis aligned bounding box. You can also try OBB. You can see this one is much better. Their previous AABB only left with 95 instances. But you can try OBB, which is the oriented bounding box. There we have 138 instances, which is much more than the AABB. And finally, you can use the convex method. And all of a sudden, the instance count jumping almost around 400. You can see this convex method gives most tightly result. And again, for OBB or ABB, there is also a 2D or 3D version here. You can debug it through this debug socket. You can see the proxy shape here. That's the proxy shape left here. You can check AABB. You will see there is no overlapping. You can check in the convex hole. You can see there is no overlapping. But if you try to debug the oriented bounding box here, you may wonder, yeah, why the OBB is overlapping? Well, why this is overlapping? Yeah, here is the information for you. The OBB may still overlapping, but their AABB are not. So internally, you will use AABB. You will use AABB to first broad detect if two instances are collide. Then if their AABB is collide, then you will check the OBB for a more finer collision detection. Because the AABB is just very efficient. And also OBB doesn't really fit the geometry as the way you want, so you combine these two methods will give you the most good result. So that's this Camera and proxy shape and 2D or 3D. And there is also a fast option here for OBB and convex hole method. This is the same, not same behavior, it's the same algorithm. So let's change that a little bit. It's using the same algorithm internally. So this one is a little bit tricky method that I've been using recast or and sample years to fix the collision detection. As you can see, the result is pretty much the same, but it can speed it significantly. You may notice that there is a little bit of wrong here. The result is a little bit jittering, but in theory, they are still not overlapping. But I don't know why it got different result in here. So that's all the options. And here we also have a camera culling. Okay, before the camera culling, for AABB or OBB, because this is a box shape, so it allows you to do some panning for the bounding box for it. For example, this is a word panning, which just defining the word unit. If you are trying to use AABB here, so if you panning it along axis, you will see that this one, the main axis here, the main x, main y here is panning here. You can panning along y, or you can panning along the positive x, positive y, positive z. So this is defining the word units. You can also try this main bound panning here. So that will just panning the corner along the diagonal line here as using this diagonal vector here and to panning this point. So if you start the main panning here, you will see that this vertex, this main position vertex is actually moving along this original the diagonal line inside of the box here. So it will be panning it along that line here. Also the maximum panning here is just moving this point, which is the max x, max y, max z here. It will be panning that point. And this is for ABB. ABB for OBB. Oriented bounding box. It will panning it again using this vertex, which is the main position vertex and the max here. But due to the box is rotating, rotated, so that may be a little bit confusing. Okay, that is way too big here. You can see that it's actually panning here. Alright, so for the maximum corner, so that's the panning option for the box. Okay, let's go to the camera culling here. So this camera culling is more advanced than you may have seen before. Because this camera culling is actually keep everything inside of the box, inside of the camera view. So for example, like you have a cube in here and you rotate it, something like that. So right now, previously, some people may checking the center point here to check the point if this point was inside of the camera or not, and based on that you will count it. But for now this point is not inside of the camera, so that may be delayed. But you don't want that because clearly we can see from the camera view we will see this box. So this one should be kept. So that one isn't working. And some of the other people may realize this instance, and they're left one point. So this cube have one point that inside of the camera view, this cube will be kept. But for example, if we rotate it like this, like here, there is no point inside of the camera view, but we still can see the cube. Other people using the point to checking if the point is inside the camera view, but here is no point, so this cube will also be delayed. But we still want to keep this instance. So in my version, this one can also be kept. So for example, I think I could join this one inside here. So let's treat this as an instance so that we can join it here. Let's see if that works or not. Yes. Let's join this as an instance. You can see after the camera culling, this one is still inside of our camera. Let's hide it. On my camera view. Okay, let's toggle the reality. Yeah, you can see this one is still inside of our camera view. That's because I used the edge to detect if this one is inside or not inside of the camera view. So that's the most accurate result. This is the most accurate method that you may see other people doing in the YouTube. So under here we have some settings. Here is the screen UV range. I should split it into X and Y channels. So if you only keep one, so here is only one range. Okay, that one. Let's get rid of this. That's the screen UV range. So right now the UV range is from 0 to 1. That's the coordinate of the point. So that's the screen UV range. If that's 1, so it will only keep this whole screen. You can also shrink it to half of our screen size. So it basically is something around this box. So once you can see this instance through this small window, that instance will be kept. You can also scale the window up. By default, size one is pretty good. And we also have a Z start here. Z start is the near plan for this camera. So for example, you want to set it to 5. So as we can see, the near plan is around here. Everything close, then the near plan will be get culling here. And we also have a start fading here. That's the fading distance. If we set it to 0, we can see everything satisfied this condition will be kept. But we can fade it a little bit so that it will gradually from 0 to 1. So here we keep nothing, and after 12 meters fading, around here. Then we will keep all the instance. So that's the fading distance. Hmm. Hmm. Same as for the end here. We have the end here. Something like 30 meters. You can make it 50 meters here. Hmm. So that's about the 15 meters. And we have the end fading. The end fading is a bit different than the previous one. From the start fading, it was fading from the near plan and fading forward. But for the end fading, we will fading it backward. So we will fade it backward. Sorry about that. So that's fading distance. Let's say again 50 meters. Okay. So I think this one is a bit too farther away. So let's try 40 here. So we will see this fading distance. If I set it to 0, we'll keep everything. And for 50 meters fading, it will gradually fading out. So from your camera view, that's it. And if we check it to 0, you can see something, but that's not very important. So you can fade it a little bit to save some performance. And pruning proxy here. So proxy, okay. Okay, I forgot that one. Let me check this. Pruning proxy. Okay, that's just for pruning it here. Pruning, oh, proxy here. Okay, that's our debug here. Let's check the debug, which is just the proxy shape. So by default, it's not pruning this one. So you can also turn this option on to pruning the proxy shape. Through the debug view, through this debug socket, you can see the proxy shape. So that will also be pruned. Here is just some random seed for the random selection. Okay, that's pretty much all the settings. Hope you enjoy it.